Alright everyone, welcome back to a new eCoreAcademy lesson. My name is Anita Raj, and I am a teacher and co-founder here, along with my younger brother AJ Raj. As you can see, this video should be familiar to you because I actually broke the last video in Algebra 2 into two parts. So this is all about practice problems. In the last video, we looked at we reviewed how to find and graph holes and asymptotes, and then we looked at some problems where we didn't have to graph and we just identified where these discontinuities occurred. In this video specifically, we're going to be looking at two graphing problems and then one word problem, things that you might encounter in the future when you're taking your assessment. So before we get into this video, I'd really appreciate it if you could like, subscribe, hit the post notification button, share using our socials, and comment down below. So let's get right into our first graphing problem number 1. And in this case, we're going to sketch the graph of the rational function y equals x minus 1 divided by 2x squared minus 2. After that, we're going to state where all the asymptotes and holes occur. And then lastly, we are going to give the domain and range. In addition, we have to show all our coordinate pairs, and we have to use an XY table to show those coordinate pairs to, show our work. So here's your solution already pre-written. I know it's kind of small, but I'm going to go through it again with you. So we're going to go through and graph this and then show all of our work. So I'm going to pull up a graph for myself. I'm going to rewrite the equation that we're going to be working with. So y equals x minus 1 over 2x squared minus 2. So first, I really want to simplify this. So what I'm going to do is I'm going to leave the numerator as is because I can't factor that, but I can factor the denominator. I can pull a 2 out, and I'll end up getting 2 times x squared minus 1. And x squared minus 1 is a difference of squares. So I'm going to rewrite the denominator as 2 times x plus 1 times x minus 1. As you can see, there's a common factor of x minus 1, so I'm going to cross that out. And what we're going to be left with is this is going to be equal to 1 over 2 times x plus 1. And if we write the new reduced function, we're going to get y equals 1 over 2x plus 2. That was pretty straightforward. Now what we're going to do is we're going to find the vertical asymptote. So the vertical asymptote is going to occur when we set the denominator equal to 0. So 2x plus 2, if we set it equal to 0, we'll find the vertical asymptote. What we can do is we can subtract 2 from both sides. So if we subtract 2, we get 2x equals negative 2. And if we divide both sides by 2, we get x is equal to negative 1. And this is where the vertical asymptote occurs. How about the horizontal asymptote? Let's check to see if we have one. Well, in this case, we're going to compare the degrees of the numerator and the denominator of the reduced function. In this case, the denominator, 2x plus 2, has a degree that is greater than that of the numerator. The degree of the denominator is going to be 1, and the degree of the numerator is going to be equal to 0. In this case, b, which is the denominator, is greater than a. And what happens when the denominator is greater than the numerator in terms of degree? Well, then we're going to have a vertical asymptote at y equals 0. Now let's look at the holes. So in regards to holes, we saw that there was a common factor of x minus 1. So if there's a common factor of x minus 1, that's where the hole is going to occur. So we're going to set x minus 1 equal to 0 to find where that hole is in regards to the x coordinate. We're going to add x to both sides and find that the x coordinate is x equals 1. Then we got to plug it into our reduced function to find where the y coordinate is, because remember, holes are points. So we're going to have the reduced function 1 over 2x plus 2, but we're going to plug 1 in for x, and we're going to get 2 times 1 plus 2. If we continue solving, we'll get 1 over 2 plus 2, because 2 times 1 is 2, and then we'll get the y coordinate, we'll find it to be 1/4. So then our hole is going to be the point 1/4. Now let's identify the domain and range. Well, the domain has to do with the x coordinate, remember our x-axis. So where do our discontinuities occur? Because that's where we're going to have unions or breaks in our domain. Where discontinuities occur at x equals negative 1, and we have where the asymptote occurs, a vertical asymptote, and then we have another one at x equals 1 where the point discontinuity or the hole occurs. So our domain is going to go from negative infinity, it's going to keep going, and then the first discontinuity is going to approach is the x equals negative 1 because the function has no value there. So we're going to put negative infinity to negative 1. Then there's going to be a union because it's going to the function's going to have a value from -1 all the way into the point 1, the whole at 1. So we're going to put that down, and then we're going to put another union, which is another break in the graph, and then we're going to have it continue to infinity with values. So note how I did include -1 and 1, the discontinuities, in the intervals, but I didn't use brackets because I'm indicating that they're not part of the domain. Then for our range is fine except this vertical asymptote at y equals 0. So our range is going to continue from negative infinity, but then when it approaches 0, it's not going to have a value. So we're going to put 0 and then a parenthesis. We're going to put a union, and it's going to continue from 0 all the way to positive infinity. So y equals 0 is the only break in the graph for the range. Then we're going to find an xy table so that we can actually plot this thing on the coordinate plane. So what I'm going to do is I'm going to start at -4. So I'm going to have -4, -3, -2. Then I'm going to have -1, which is going to be undefined, because that's where my vertical asymptote, undefined, because that is where my vertical asymptote is going to occur. Then I'm just going to have three more points actually after it, 0, 1, and 2. And then we're going to plug each of these points into the reduced function. And when we do that, I'm just going to, just for the sake of time, hopefully you know how to do that. So 1 over 2 times -4 is -8 plus 2. It's going to be -1/6. So if you do that, you'll get -1/6 for -4. You'll get -1/4 for -3. You'll get -1/2 for -2. For 0, you will get 1/2. For 1, you should already know we're going to get 1/4 because this is where our whole occurs. And then for 2, we're going to get 1/6. And then what we're going to do is we're going to plot these on this graph. The first thing I like to do is I like to indicate where my asymptotes are. So I have an asymptote at y equals 0, so I'm going to dash the x-axis like this to represent the asymptote. I have another asymptote at x equals -1, so I'm going to dash x equals the vertical line, x equals -1 like that. Then I'm going to first plot, the first point I'm going to plot is my whole, which is 0, 1 1/4, so that's going to be right here. Then I'm going to start from the top and go to the bottom. So at -4, we have a whole at -1/6. At -3, we have a whole at -1/4. And then at -2, we have a whole at -1/2. Then we're going to skip over the vertical asymptote, over the whole to 0. So at 0, we have a point at 0, 1/2. And then we have the whole, which we already graphed, and then we have a point at 2, 1/6. And then afterwards, it's just a matter of connecting these dots. So I'm just going to sketch a graph like that along the asymptotes, trying to represent that this graph approaches the asymptote, increasingly approaches the asymptote, but it's never going to touch the asymptote. And there you have your first graph. All right, so let's move on immediately to the next problem. So we're going to sketch the graph of the rational function y equals 3, just the constant 3, divided by x minus 2 times x plus 3. Afterwards, we're going to state all asymptotes and our wholes, which are our discontinuities. Then we're going to give the domain and range, and then we're going to show our coordinate pairs on an xy table next to the graph. So here's your solution already pre-written. I know this graph looks a lot different from what we've worked with because you see kind of a parabola, a reflected parabola at the bottom. It's not a parabola, but it definitely looks like one. And then you see it's actually really pretty, I thought. But the thing that is to note about this graph is that it has 2 vertical asymptotes, and that's what creates this bizarre shape we've never seen before. So let's discuss how we are going to do this problem. So I'm going to rewrite the rational function we're working with at the top, which is y equals 3 divided by x minus 2 times x plus 3. As you can see, we can't really reduce it because the denominator is already factored and the numerator is just a constant, so we're not going to reduce it or anything. We're going to immediately jump into finding the vertical asymptote. So the vertical asymptote is going to be equal to, well, we're going to look at the denominator, set it equal to 0. In this case, we have 2 factors, so we got to set both of these equal to 0. First, we're going to set x minus 2 equal to 0, add x to both sides, and find the vertical asymptote at x equals 2. Then we're going to find the second vertical asymptote, which is x plus 3. You can't forget that one. We're going to set it equal to 0 and find the second one is going to be at -3. Afterwards, we're going to go about finding the horizontal asymptote. In this case, we have to compare the degrees of the numerator and denominator. To do that, we actually have to we have to FOIL the denominator, so we got to multiply it out. So if we multiply x plus 2 times x x minus 2 times x plus 3. X times x is x squared. X times 3 is going to be 3x, minus 2x is just going to be x plus x, and then negative 2 times 3 is going to be negative 6. So this is what our denominator would be. It's a quadratic trinomial with a degree of 2. Our numerator is 3, which is just a constant term. So the denominator is going to have a higher degree than the numerator, meaning we're going to have a vertical asymptote at y equals 0. And then we're going to look at wholes. However, as you can see that we had no common factors. So we couldn't reduce this, and we also couldn't find any common factors between the numerator and denominator. When there's no common factors, that means there are no wholes. So we don't have to worry about wholes for this problem. Let's find the domain and range now. So as you can see, the domain is regarding discontinuities with x. We have two vertical asymptotes, one at x equals 2 and one at x minus 3. So we have to take those into account. So from negative, the function is going to continue from negative infinity, and it's going to hit this discontinuity at x equals negative 3 first. So we're going to have negative infinity to negative 3, put a parenthesis. Then we're going to continue from negative 3 until we hit 2, where there's another discontinuity. And then we're going to have a union from, actually I'm going to write it down here. And then we're going to continue from 2 to infinity because we won't have any more discontinuities in regards to the domain. For the range, we have only one discontinuity at y equals 0. So it's going to be the same as the last problem. We're going to continue from negative infinity to 0. Then we're going to have a union because there's a horizontal asymptote at y equals 0. And then we're going to continue to infinity. Okay, now let's make an xy table. And we're going to put points in this xy table so that we can actually graph. For this problem, it's a bit complicated because what you'll see is that if you plug values into the function, you're going to get a lot of decimals. So what you can do is you can actually pull out your calculator. You can go to your y equals. You can type in this. You can type in the rational function. So 3 divided by x minus 2 times x plus 3. And then what you're going to do, you're going to have that typed into your y equals. And there's a bit of a glare, but you're going to have that typed into your y equals. And then what you're going to do is you're going to hit second, and then you're going to hit graph. And above graph is a table. And then suddenly you're going to get a table. I know it's kind of hard to see, but I'm not showing you because we should be able to do it at this point. You're going to get a table, and you're going to get decimal values. So you don't actually have to do any of the math. The calculator will do it for you, and you'll see that there are errors at x equals 2 and x equals negative 3 because there are asymptotes there. So that means you typed in this function correctly. So now what we're going to do is we're going to use our calculators, and we are going to we're going to find the coordinates we want to plot. So, for example, we're going to start negative 6, and then at negative 6 we have 1/8 as a point. Then we have negative 5, 0.2143. Negative 4 we have negative 1/2. And negative 3 we have our asymptote, so it's undefined. And we're just going to write we have an asymptote here to remind ourselves that we do. Then we have negative 2, which is negative 3/4. And then at negative 1/2, I'm going to skip to negative 1/2 just because of the way this graph is like structured. So I'm going to skip to negative 1/2. We have 0.45 as a corresponding point. I'm going to continue this xy table over here because there are a few more points I want to plot. And then at, where were we at? So negative 1/2. Then at 1, we're going to have negative 3. Oops. Then at 1, we're going to have negative 3/4. At 2, we're going to have our vertical asymptote. So it's going to be undefined at 2. And then at 4, I'm just going to write these points up here. 4, we're going to have 0.2143. And then at 5, we're going to have 1/8. The reason I'm putting so many points down is because we want to have enough points that surround those vertical asymptotes. So because we have 2, we need like almost double the amount of points so that we're representing the entire graph with all the curves and everything we need in it. All right, so now we're going to get to graphing this. So we're going to first show our asymptotes, y equals 0. So I'm going to dash here. And then we have another vertical asymptote, a vertical asymptote at x equals 2. And then we have a vertical asymptote at x equals -3. X equals -3 like that. Now we're going to plot these points. So our first point is at -6, 1/8, which is here. Then we have a point at -4, 0.2143, which is about 1/5. Whoops. We have a point at -1/5, and then we have, 1/5. Then we have a point at -4, -1/2. Sorry, this shouldn't be -1/2. This should be 1/2. Actually, no, it should be -1/2. My bad. These graphs can get kind of confusing. Actually, no, it should be 1/2. My bad. 1/2. You can see even I get kind of puzzled by these. 1/2. And then we have our vertical asymptote, and then we have -2, -3/4 as our next point. As you can see, it drops down here below the y-axis. So that's where we're going to get the second curve. So -2, -3/4. Then we have -1/2, which is going to fall right here, 0.45, which is about 1/2. -1/2. I'm just checking my work. Should be up here, actually. Okay. So at -1/2, we should actually have a -0.45. Sorry, in my previous work on that other table, it showed positive. It should be -0.45. And after that, we're going to plot. After that, we're going to plot 1, and then it's going to be at -3/4, so the same as x equals -2. Then we can just sketch this curve, actually, and then sketch that half. And then this curve is also done, so I'm just going to sketch that like that. And then we're going to continue plotting these points. At 2, we have an undefined vertical asymptote. Then we have another point at 4, 0.2143, which is about, actually, I skipped 3. I skipped 3 by accident. Should have a point at 3, 1/2. So 3, 1/2 is here. Then we have another point at 4 and about 1/5, and then another point at 5, 1/8. This is going to be our other curve, like so. All right, so I know that was a difficult problem, but we got through it, and that's all the work. And for our last word problem, so we're looking at saline concentrations in a pharmacy. We're going to try to incorporate a real-world application. So you work in a pharmacy that mixes different concentrations of saline solutions for its customers. So saline solutions have different concentrations in them of how much saline they have in them, because they are solutions, so they have a dissolved component. The pharmacy has a supply of 2 concentrations. We have a 0.5% and a 2%. The function y equals 100 times 0.02, which is going to be 100 milliliters times the 0.02, which is the 2%, plus x, which is an unknown amount of milliliters, times the times the 0.5%, which is 0.005. All of that divided by 100 plus x, which is the 100 milliliters of the 2% plus how many milliliters we have of the 0.5%. This gives the concentration of the saline solution after adding x milliliters of the 0.5% solutions to 100 milliliters of the 2% solution. How many milliliters of the 0.5% solution must you add for the combined solution to have a concentration of 0.9%? This might be long-winded and it might seem difficult, but it really is not, so just stick with me. The first thing we're going to do is we're actually going to use a calculator for this. So we're going to use the graph. Actually, I want to show you the solution before I actually start writing. So here's your solution pre-written. We're just going to go through that again. It's actually a very straightforward problem that I'm going to go through pretty fast. So we're going to use our graphing calculator. First, we're going to take this 0.9% that we want to find, and we're going to turn it into a decimal. So what we're going to do is we're going to take 0.9 and then divide it by 100. And then we're going to find that we're pretty much working with the decimal 0.009. So we're going to use our y1 and our y2 in our calculator. In our y1, we are going to put in 0.009 because that's the value we want. So we're going to have a horizontal line. And then in our y2, we're going to actually plug in this equation that they've given us in the problem. So 100 times 0.02 plus x times 0.005 divided by 100 plus x. What we're going to do now is we're going to graph both of these, and then we're going to find the point of intersection on the graphing calculator. So when we do that on graphing calculator, so when I do that, I'm just going to plug these in my y equals. So I'm going to go to my y equals, plug in 0.009 in y1, and then in y2, I'm going to plug in 100 times 0.02 plus x times x times 0.005, and then I'm just going to divide that by 100 plus x. And then all you're just going to do is you're going to hit graph. Then you're going to see what happens. You're probably going to have to adjust the window, but you're going to have to adjust the window, and then you're going to hit second calc, and then you're going to hit 5 for intersect, and then you're going to find the intersection. And then once you find the intersection, you should be able to find that the intersection occurs at 275, 0.009. It's going to be a point. So yeah, it's going to be a point. And at 270, this 275 is actually your answer. It's the amount of milliliters you're going to need of the 0.5% solution. So 275 milliliters is going to be your final answer to this question. Pretty simple. It's not too much, just using a graphing calculator. Alright, so that's all I have for you. I hope you enjoyed the lesson. It was just a continuation of the last one, but I wanted to break it up into 2 bite-sized pieces for you. If you enjoyed, please like, subscribe, hit the post notification bell, drop a comment down below, and share. You can also check out our website and our Gmail. Thank you for watching.